to the next speaker, which is Rebecca Levy, postdoc from University of Arizona. She will present the result on the morpho-kinematic architecture of superstar clusters in the center of NGC253.
Great, thanks. Thanks to the organizers for allowing me to talk to everyone today, and thanks to everyone for coming. So yeah, my name is Rebecca Levy. I'm an NSF postdoctoral fellow at the University of Arizona, and I'm really excited to talk to you today about some recent work that I've been doing with some high-resolution ALMA data, looking at the morpho-kinematic architecture of these superstar clusters in the center of NGC253. On my title slide, I'm showing NGC253, and the region that I'm primarily going to be focusing on today is in this little tiny box that's blinking in and out at the very heart of this galaxy. But before I dive into this, I want to make a quick plug for a paper on a different topic that just appeared on the archive today. This is a paper led by a student who is working with me, Lauren Cook, and also uses ALMA data. So if you're interested in dark matter and dwarf galaxies, I just wanted to give a quick plug for this paper, again, that just appeared today on the archive. But going back to NGC253, NGC253 is a really special galaxy. It's extremely nearby, and it's what we call a starburst galaxy. This means that the very center of this galaxy, roughly the central kiloparsec, which I'm showing here in this pink box, is forming stars at a very high rate. The star formation rate in the center of this galaxy is about 2 solar masses per year, which may not sound like a lot, but that's roughly equivalent to the star formation rate of the entire Milky Way galaxy, but condensed down into this very central region. And we think that this central starburst is being fueled by gas inflows along the bar that you can see in this near-infrared image. So if we zoom into the center of this galaxy, where all of this star formation is happening, this is what the central just few hundred parsecs of the galaxy looks like in ionized gas. This is looking at Paschen alpha data from the Hubble Space Telescope in the background. And in the late 90s, there were 4 near-infrared clusters identified, shown here in the red circles. And later on, this one down here was identified to be a superstar cluster. So what exactly is a superstar cluster? A superstar cluster is just a very massive, very compact, very young cluster of stars. In particular, superstar clusters have masses, stellar masses in excess of 100,000 solar masses, and they have sizes of order a parsec or less. So these are very extreme objects, and unlike things that we have in the Milky Way, for example. But given the intense star formation that we know is happening in the center of this galaxy, we would expect to see many more superstar clusters than just this one. And the reason why we don't see them in the near infrared is because there are 30 magnitudes of extinction to the center of this galaxy in the near infrared. And that's more than enough dust to obscure an entire population of superstar clusters below it, especially if these clusters are still young and very gas and dust rich. So in order to reveal this population of clusters, we have to push to longer wavelengths where we can instead see this dust and dense gas in emission. So this was first done using the submillimeter array by Sakamoto et al. In 2011. This image and all of the images I'll be showing from here on are at a wavelength of 850 microns or 350 gigahertz. And at this frequency, the continuum emission is primarily tracing thermal emission from dust. So here in this image, you're seeing the sort of GMC scale warm dust, indicating that there's lots of warm molecular gas around. And these are the sites of this intense star formation, which you can see are not visible for the most part in the ionized gas map. But again, to reveal the actual clusters themselves, we need to push to higher angular resolution. And this is where ALMA has really revolutionized this field of study. So this was first done in ALMA cycle 2, where now you can see we've drastically improved the angular resolution, and now we can start to see these clusters emerging. We can push to even higher resolution with ALMA. So this is now 2 parsec resolution data. And what was shown in this paper by Leroy et al. From 2018 was that these 14 clumps of dust emission have all of the hallmarks of a population of superstar clusters in the process of forming. Now, this data set is amazing, and there's lots of things that we can do with it. But if we want to spatially resolve these clusters to measure their sizes and their masses more accurately, we still have to push to higher resolution, because even at 2 parsecs, these things are still only marginally resolved. And so this is work that I led last year. This is now half a parsec resolution ALMA data, still looking at the dust in this same region. And you can see that what were previously blended structures now separate out into discrete points. And these are the population of superstar clusters, which we can now spatially resolve. I won't stay on this for too long, but one of the key results from my work from last year was that we discovered that 3 of these superstar clusters have outflows of dense molecular gas. So the insets I'm showing here show the CS7 to 6 spectra towards 3 of these clusters. CS7 to 6 is a great tracer of dense molecular gas. And you can see that the line profiles have a really interesting shape, where there's this blue shifted absorption and red shifted emission, and this is characteristic of outflows. So I won't talk about these anymore, but I'm happy to answer questions about the outflows from these clusters. But really what I want to talk about today is, why are the clusters located where they are in the center of this galaxy? How does this relate to how the gas is being funneled down to the center? And how are these clusters arranged in 3 dimensions? It's worth noting that these clusters, these 14 plus or minus however many little subclusters pop out, these clusters can explain 100% of the star formation in the central starburst of this galaxy. And so most of the star formation is proceeding in this very clustered manner, concentrated in just the central 150 parsecs of this galaxy. So zoom out a little bit, let's talk about how gas flows from the bar down to the center. So here's again the near infrared image of NGC253. You can see it has this bar oriented like this. Now, sort of schematically, gas will flow in from the outer regions along this bar and concentrate in the center. But if we want to compare this to our data, we need to be a little bit more precise. And so there's a couple ways to think about how gas flows and collects in a barred potential. So one way to think about this is in terms of resonances. The bar of this galaxy is rotating, and this sets up a series of resonances where gas will collect. And so I'll zoom in a moment. But here I've overlaid in the colored ellipses just the locations of a few of these important bar resonances. Another way to look at this is in terms of the bar potential itself. So if you can make a model of the potential of a galaxy with a bar in it, you can calculate the orbits that gas and material will take in that potential. And what comes out is there are 2 families of orbits that exist in this bar potential that are driven by the bar. The first ones are what I've drawn in red here. These are parallel to the bar. These are called the X1 orbits. And then there's a second family of orbits on smaller scales that's perpendicular to the bar. And these are called the X2 orbits. And these orbits are what allows this gas to be funneled down to the center. So now zooming into the center a little bit more, what's interesting to compare with our data is, so the gray boxes here show the field of view of our ALMA data, so the central 280 parsecs of this galaxy. And what you'll notice is this innermost bar resonance, again, where gas is expected to collect, is at least on the same size scale as the ALMA data that we have. And I'll note that this circle down here is the beam size of the data that were used to derive these resonances. And so things on this scale are quite uncertain. But the fact that there's sort of an agreement there is really interesting. In terms of the orbits, gas will start to, will be flowing in along these X1 orbits. And I'll note that here I'm just showing the outermost and the innermost orbits. There are orbits in between these. When the gas hits this sort of intersection point between the X1 and the X2 orbits, it will shock and it can transition from an X1 orbit down to an X2 orbit and flow down into the center. And you'll notice that this innermost this innermost X2 orbit is again about the same size as our ALMA data. So we can plot the locations of these orbits and resonances over top of our data. So here I'm showing in the colored circles are the locations of the primary or most massive and largest superstar clusters in the center of NGC253. And here they're color coded by their velocity. The spectra that we get from ALMA are extremely rich in terms of the line species that we detect. And so this allows us to put really tight constraints on the velocities of the clusters themselves. And so what you can notice is that this pink dashed ellipse is that innermost X2 orbit, where again, this gas is thought to collect and sort of pile up. And so this agrees remarkably well with the locations of these superstar clusters. And so this is really strong evidence that these clusters really are forming at the precise locations where this gas that's being funneled in from larger scales is collecting and piling up. Now this evidence gets even stronger if I now plot the dense molecular gas in the background. So the background here is showing the CS7 to 6 velocities. And so you'll notice that these superstar clusters are aligned very well in terms of morphology with the dense molecular gas and in terms of velocity. So this is a really interesting and tantalizing hint that the gas finally becomes dense enough at this innermost X2 orbit to produce something like CS7 to 6 and can then collapse further to produce these very compact, very massive young star forming regions. So now we know, at least we have an idea of why the superstar clusters are where they are in the galaxy, but this doesn't quite answer how they're actually arranged in 3 dimensions. And so to look at this, I started with models that were developed for the central molecular zone of our galaxy, the Milky Way. And so there's a long history of developing these orbital models to explain the orbits of the massive star-forming regions in the center of our galaxy. And there are actually a lot of similarities between the central molecular zone of the Milky Way and the center of NGC253. So in the interest of time, I'm only going to talk about 2 of these models that I fit, but there are 4 in total that I've been looking at. The first class of orbital models is what's called a closed orbit. So these are ring-like orbits that you can see here where there are no open ends. And this one that I'm showing is of a twisted ring, which was developed by Molinari et al. And explains the orbits of material in the CMZ quite well. So I'm showing in this, great, thank you. What I'm showing in this 3D view is sort of the galaxy-centric view of this orbit, where the observer is over here. This X coordinate corresponds to galactic longitude. The Z coordinate is galactic latitude, sort of out of the midplane. And then the Y coordinate is the line of sight of the observer through this structure. The color scale is showing the radial velocity of material along this orbit. And then things that are outlined in blue show just the front side of the orbit, and things that are in red show the back side of the orbit from the point of view of the observer. Now, in addition to these closed orbits, we can also have open orbits. And so these have sort of these open-ended streamlines on the end. And given that the mass distribution in the center of this galaxy is extended, it's not concentrated in a point on these size scales, an open orbit is perhaps dynamically more likely than a closed orbit. So these are also an interesting family of models to consider. And so this one that I'm showing here is sort of this twisted pretzel-like structure, which is a hybrid between this twisted ring model and a stream model that was developed by Kreuzen et al. In 2015. And so given these models, we can change the input parameters to better match our data. And then we can project these models into a position velocity space to better compare with our superstar clusters and the measurements that we have. So here's an example of what that looks like for these 2 models. So here I've projected those 3D models into right ascension and declination space on the sky. And again, the color coding is by the velocity that you would observe. And so you can see that for both of these models, the agreement with the positions and crucially the kinematics of the superstar clusters is quite good. It's not perfect, but both of these models do a pretty good job of describing how these clusters are arranged in 3 dimensions. And again, I want to emphasize that the kinematics here are really key because this galaxy is edge on, and so separating things just in terms of morphology is really difficult. So I'll just summarize very quickly. I want to emphasize that currently only ALMA enables us to resolve the superstar clusters in the center of this galaxy, and that ALMA has really revolutionized this study of massive star formation in galaxies outside of our own. And that in the future, instruments like the NGVLA will also play a very key role in studies like this. So our main results are that we find that the bar resonances and orbits are aligned with the superstar clusters that we observe. And this strongly suggests that the bar drives this gas down to these scales and explains why the superstar clusters are located where they are. And finally, we find that the superstar clusters are morpho-kinematically consistent with either being a ring or a crossing stream, although we can't quite distinguish between those two. And I'll just note that we have an approved cycle 1 JWST program to observe this galaxy and these clusters, and these data might be able to help us distinguish between those two. So I'll stop there and I'm happy to take any questions. Thanks.
Thank you very much, Rebecca. It's a very clear representation on the morphology and kinematics of SSE in this galaxy. I'm very curious about the outflow that you see in some of the SSE.
Mm-hmm.
Can you say something more about the properties that we are able to extract from the available ALMA data?
Yeah, so I'll just briefly talk about those a little bit. So these outflows were revealed by this very high resolution data. We've looked back in sort of the lower resolution data, and there's a hint of them there, but nothing that you would ever claim is an outflow from those data alone. So we know a lot about these outflows, and in particular from cluster 14, which is the strongest detection. So these outflows have a mass outflow rate of about 10 to the 5 solar masses. That's pretty uncertain number, but that's a huge fraction of the gas mass of these clusters. So these outflows will have a really substantial effect on the star formation ability of these clusters going forward and on their star formation efficiency. Their star formation efficiencies. We performed some modeling to try to constrain the geometry of these outflows. And we find that these outflows have to be mostly spherical, or at least very wide angled. So this is in agreement with a lot of recent numerical simulation work that shows that outflows from clusters like these should be roughly spherical. But it also explains, or at least rules out, that we're not missing outflows from other clusters because of a geometry effect. And finally, we can try to, given the velocities that we measure for these outflows and the momentum carried by them, we can try to place constraints on the physical mechanism that's powering the outflows by comparing to simulation and analytic work. And we find that these outflows are probably driven by some combination of stellar winds from massive stars or by dust reprocessed radiation pressure. So this is radiation pressure from the central stars in these clusters that's been absorbed by dust and then re-radiated in the infrared. To be honest, none of the mechanisms work to completely explain all of the clusters. So this is still a bit of an open question, but those are the most likely sources powering these outflows.
Thank you. Very impressive. I think we have some questions.
Yes, but there is a more general question, which is what is the relation between the giant molecular clouds and the SSCs? Are those SSCs inside the GMCs or are they separate?
They're inside the GMCs. So these things are hierarchical in nature. So these clusters are embedded deep within these GMCs that have been detected before. You're not seeing them on the scale because the interferometer filters out that large scale structure, allowing us to see the very small scale structure in these data.
Then there is a question related to the outflow discussion you were having. What do you mean by outflows at this scales objects? I come from star formation, and for me outflow means something very collimated and that doesn't look like that spectrally.
Yeah, so this is from star formation. It's not a collimated outflow. It's sort of if you want to think about it as like a stellar wind or an expanding envelope, sort of a thing. Again, they're mostly spherical, but these outflows are fast and very massive. relatively fast, not like a galaxy scale outflow, but this one, for example, has an outflow velocity of about 25 kilometers per second. And so they're not collimated, but they are carrying away a lot of mass and momentum from these structures, and hint that these three clusters are in a different evolutionary phase than the other clusters that we see in this burst, with cluster 5 likely being the oldest cluster. It's also the only one that's seen in the near infrared, which is interesting.
Yeah, another question was wondering if this was actually an outflow or a galactic wind that is traced by the absorption against the SSCs.
No, so this absorption that we're seeing is so expanding shell around the clusters themselves. This galaxy does have a galactic outflow, which is also thought to be, or which we know is driven by the starburst, but it's not, physically connected to these outflows. These outflows aren't directly powering the galaxy scale outflow that we see from the center of this galaxy.
Yeah. I think there are other questions, but I think the discussion can continue on Slack.
Yes,
Yeah, I'm happy to take questions there.
Thank you very much.